Welcome grade 11s to this physical science lesson. My name is Gillian, and today we're going to be looking at the big picture, the big ideas around energy of chemical change. Now, you've had a chance to look at some of the videos this week, and so we're just going to look at those really important ideas that are coming out of this topic. If we look at the concept map, you will see that we have to start with bond energy that we need to discuss, and we will be doing that in some detail. Then we're going to have a look at enthalpy change and what that's going to look like on a graph as well as in calculations. We will have a look at energy profiles, and energy profiles tap into types of reactions, and they will change, the energy profiles will change as the types of reactions that we're looking at will change. We're going to have a look at exothermic reactions, those that release heat, and endothermic reactions, those that absorb heat to be able to happen. We also will have a look at spontaneous reactions and non-spontaneous reactions, and then we will check out catalytic reactions and what those look like and how the profile will change, the energy profile will change. So activation energy is the one that's left out, and activation energy we will speak about in terms of the energy profiles and what that looks like. Law of conservation, we will have a look at that too. So let's start with bond energy and what bond energy is all about. So when a reaction, a chemical reaction happens, the reactants that are involved have to absorb energy to be able to react. Those bonds that keep the particles together have to be broken. And you may have come across this. There are different types of bonds that happen, different types of bonding, covalent bonding, ionic bonding, metallic bonding. And those bonds, when they happen, there's energy that is trapped within them, and so they have to be broken. So on the screen you'll see I have a reaction here. It is hydrogen plus oxygen, which creates water, which produces water. Now, hydrogen is a diatomic molecule. It comes as H2, and it is covalently bonded, and you can see this little picture here. There's one of them there, and we have to break, or the reaction has, the bond has to be broken in order for the reaction to take place. The same applies for oxygen. Now, oxygen has got a double bond. It is also a diatomic molecule. It's covalently bonded to itself, and those double bonds have to be broken. So you can see here that energy has to be put into the system to break those bonds apart. Now, the interesting thing is that when new bonds are made, as in the new water molecule, here we go, is made, energy is actually released, and it's called the energy of formation. So this energy that is required, that is absorbed to break bonds, we will later come to know as activation energy, and we require quite a lot of it. And then the energy that is released is bond formation. So energy of bond formation. So what do we have to do with these bond energies? The ones that are trapped, the energy that is trapped within a bond and has to be broken apart when we are wanting a reaction to happen, and the energy that is released when new substances are formed. Now remember that physical change doesn't require such huge amounts of energy. In fact, it requires only a little bit of energy, and no real new products are formed. In a chemical reaction, however, a chemical change, energy is required. It is a huge amount of energy compared to that of a physical change, and it is very difficult to reverse that reaction. So chemical change all revolves around energy. So we can work out the amount of energy that is needed to break the bonds, the energy that we would later come to know as activation energy. Scientists have gone and checked out these energies that are trapped within the bonds very specifically, and so we get what is called the bond energy table. And here we can see that I have specifically the bond that we're speaking about. So hydrogen-hydrogen bond, an oxygen bond, and you can see that it's a double bond, and then the oxygen-hydrogen bond. The energies are here, and you can see they're really specific. Energy is measured in kilojoules per mole. There it is there. That's the unit. And you can see here that these are very specific energies that for that particular bond between those particular atoms. The first thing that we do, or have to do, when we are trying to calculate these energies is we have to balance the equation. Now, there is a conservation of mass and atoms when a reaction happens. And so the number of atoms that are involved in the reaction need to correlate to the number of atoms that will form the new product. So that is why we have to have a balanced equation. And so that is why I have two hydrogens here. There's the first hydrogen and there's the second hydrogen. Why? Well, we have got two oxygens. So we have got O2, we've got two oxygens there. And for the specific water molecule, we have got one atom of oxygen bonding to two atoms of hydrogen. And so to balance that equation, we need to have two hydrogen diatomic molecules reacting with one oxygen, and it results in two water molecules. And so it is all balanced. You can see there 1, 2, 3, 4 hydrogens, and 1, 2, 3, 4 hydrogens on this side. There are two oxygens on the reactant side, and there are two oxygens on the product side. So the reaction has to be balanced before we can do this. So what about energy of breaking bonds? So we have got two hydrogen diatomic molecules. Over here, we are given the bond energy for only one. So we have to times that by the number of atoms that we have, or the number of bonds that we have. So let's pop this in. It's 4, 3, 6. Okay, let me just rewrite that. 4, 3, 6. That is the amount of energy it's going to take to break one hydrogen-hydrogen bond. How many do I have? I have 2, so I have to times that by 2. So I have to do it in the ratio of the reactants. Oxygen, I have to break up the oxygen molecule as well. There's only one of them, and so there will be my bond energy from the table, and if I calculate that, it will end up being 2,239 kilojoules per mole. What about forming bonds? Now, we've already said that when products are formed, bond energy is actually released. There's energy that is released. So this energy of forming bonds is the released energy. We can say that that is negative because it is being given out, whereas the energy that is absorbed, we can say it's positive because it's being taken in. So sometimes we write this energy as a negative value because it is energy that is being released when those new bonds are being formed. Let's have a look at how we calculate this. So our hydrogen-oxygen relationship has got a value of 463 kilojoules, and in one molecule of water there are 2 of those bonds, but we have got 2 water particles, water molecules. So we're going to say 2 times 2, which is 4, and so our total amount of energy which is released is 1,852 kilojoules per mole. Right, so that is energy that is released when those bonds are being formed. When we look at the overall picture of a reaction, there is definitely a net energy that is involved, and this energy, this change in energy that occurs is called the heat of reaction. And what is that? Well, that is the measure of enthalpy change. So energy changes that happen in a reaction as the reactants are changing into products, that is called the change in enthalpy or the heat of reaction. It is the net, it's the overall energy value of the reaction. So we can calculate this when we are not given a graph. So when we do this, we need to use some understanding. We need to use our understanding of how the bonds are broken and how the bonds are formed to be able to solve problems around calculating this enthalpy change. So let's have a look at this reaction that I have here. It's the same one. What are we going to do now? Well, if it's a change, it is a difference. A change is a difference in energy. So we've already calculated that for the reactants, we have a value of 2,239 kilojoules, and for the water, we have a value which is 1,852. This is energy which is released. So if we find the difference, we could say 2,239, subtract, because that's the difference, 1,852. And we end up with an answer here of 387 kilojoules per mole. If we consider this energy for formation of water to be negative, which fits in right there, negative, then that will be the correct answer. It's going to be a positive answer. If we use our reasoning to look at this, we can see that the energy that is absorbed is greater than the energy that is released. And so we would have to get a positive answer for this enthalpy change, the overall change in enthalpy. Right, I think that we have had enough time. We need to give our brains a little bit of space to process all this. We are going to take a break now. Welcome back, grade 11s. Let's continue. We've spoken about bond energy, and now we're going to move on to energy profiles. Before we do that, we need to brush up our knowledge on the law of conservation of energy. Remember that energy cannot be created or destroyed, and so this is not energy that we are conjuring up. Okay, it comes from somewhere and it will be transformed into something else. Right, so if we have a look at our mind map, our overview, we are now going to have a look at what is an energy profile and how does that look when we specifically are looking at different types of reactions. So what exactly is an energy profile? Well, an energy profile is tracking what is happening with the reactants and the products and their energy as the reaction progresses. So if you look at this graph, it is just a set of axes at the moment, and on the x-axis you'll see that there's a progress of reaction. So as it starts, nothing is happening, and then it starts moving forward. What will happen to the energy of those particles, molecules involved? So an energy profile shows the changes of the reactants moving to products in the reaction. And when we look at matter, we'll see that all matter has a certain amount of kinetic energy. So what will this profile look like? This is just going to be a general feel for what the graph is going to look like. We start with the reactants on the y-axis over there. Generally, there has to be an increase in energy. We speak about activation energy, and then the products are formed and they will have a certain amount of energy. So over here on the y-axis, you'll see that our reactants have a very specific energy. That's for a specific reaction when it is accurately measured. And when you see this type of graph, there will be a number there, and that is the specific energy of the reactant in that particular reaction. For the product, the same will happen. If we draw a line across and we read off the graph over there, we will get a specific energy for the products in that specific reaction. So how do the different reactions look, and what is important in each one of them? Activation energy is really important. So that's the energy of breaking bonds. If energy is insufficient to break the bonds, this reaction will not happen. On the graph here, you can see that the blue arrow is indicating from the reactants right to the very top of that curve, and that is the activation energy. It is the minimum amount of energy required to make a reaction happen. If not enough energy is absorbed, nothing's going to happen. Its symbol is EA with a little a, and because we are talking about energy, its units is in kilojoules per mole. The activated complex is a really interesting concept. So here on this graph, you can see that little pink dot. It is a system which is in flux. It is unstable, it is fragile, and it's this mishmash of reactants being broken and products being made. So that is what we call the activated complex. So what does the energy profile for an endothermic reaction look like? Well, an endothermic reaction absorbs heat from the surroundings. It needs energy. So if you touch that reaction vessel, it might even feel slightly cooler or even cold if it's quite a hectic endothermic reaction. So endothermic reactions, they need heat. So heat is absorbed, or energy is absorbed. Energy is absorbed. Its profile is interesting. So our activation energy from the reactants is right to the top. You can see it here, activation energy. It's the energy which is absorbed. And then to form the products, energy has to be released. And here we have the products, and you can see that the products have a greater energy, if we read it off the y-axis, a greater amount of energy than the reactants. So that is telling us that the change in enthalpy, or the delta H, is going to be a positive value. It's going to equal a positive value, and that is a very definite sign that we have an endothermic reaction, because it absorbs heat. The products have they release less heat than is absorbed, or less energy than is absorbed, and so there will be a product that has got a higher energy on the y-axis than the reactants. So when we get this delta, I'm just going to erase what I've written here. When we get delta H being greater than 0, in other words, a positive value, we know that it's going to be an endothermic reaction. If we move on to the exothermic reaction, it is very different. Although the shape of the graph and the energy profile is the same, it is quite different. We can see here that the products are releasing a lot of energy when they are being formed, and so the product on the y-axis will have a less value of energy than the reactants. A great amount of energy is released. We will feel that the container is warm or even hot. So energy is released into the environment. So the overall energy of the system, the overall enthalpy, the change in enthalpy, is going to have a negative value. So it is going to be equal to a negative value, and delta H then is going to be less than 0. So that tells us that we have an exothermic reaction, that the energy released when bonds are being made is greater than the activation energy that is absorbed by the reactants to break those bonds. What is then a spontaneous reaction? Well, a spontaneous reaction will happen at a temperature which is lower than room temperature. A non-spontaneous reaction needs energy to be given to that reaction. It will not happen at room temperature. It has to happen at a higher than room temperature. A catalyst is a really interesting chemical that can be added to a reaction. So this chemical doesn't participate in the reaction, but it does a very strange thing. It lowers the activation energy needed for the reaction to take place, and it offers a different energy route for the reactants. So if we look at this energy profile, you can see that there is a dotted line, yellow line here, and that is what the catalyst will do. It lowers that activation energy and provides a different path for the reactants. It does not in itself change chemically. Now, this is the kind of question that you might be asked. You can answer it in two different ways. You can see it in two different ways. You are given a balanced equation, or even an equation that is not balanced. You have to find out whether it is going to be an exothermic or an endothermic reaction using the table of bond energies. So you are going to do it exactly like we did it before. You can either use the energy of formation as a negative value. You can plug it in, or you can use your head, your reasoning, and you can find the difference in the bond energy of the reactants and the bond energy of the products. In other words, you're finding the change in enthalpy, and if the one is greater than the other, you will know that it is that kind of reaction. So if it's positive, it is going to be an endothermic reaction taking in energy, And if it is a negative value, it's going to be an exothermic reaction, releasing energy to the environment. I hope grade 11s that has helped you get the big picture around chemical change involved in, or the energy involved in chemical change. We hope to see you next time.